Hello everyone. In this video we're going to learn about the rate of change of one variable with respect to another variable and see how that ties in with the concept of the slope of a line, which we are familiar with from algebra. So the formula that we use for rate of change is quite intuitive. So if we want to find out the rate of change of y, the variable y, with respect to the variable x, remember that we use y to represent the response variable and x to represent the explanatory variable. So we want to know what kind of a change the response variable goes through when the explanatory variable goes through this kind of a change. So basically, when the explanatory variable changes from x1 to x2, what does the response variable change to? As we can see here, it'll be from y1 to y2. So the quotient of the ratio of this change in the response variable to this change in the explanatory variable is what we consider to be the formula for the rate of change of y with respect to x. So we basically divide the change in y by the change in x, and if you remember, the change in y is just going to be the final value of y divided by the initial value of y, so y2 minus y1, and the change in x is going to be the final value of x minus the initial value of x, so x2 minus x1. This nice simple formula will give us the rate of change of one variable with respect to another, in this case y and x. Now remember, in statistics, depending on the situation, we may use a different letter to represent the horizontal axis, such as t, right? Or a different letter for y, such as percentage. So we will be flexible and use different letters as the need arises. Okay, so for our first example, we're going to look at a rate of change. The number of pedestrian fatalities in the United States declined approximately steadily from 4,795 fatalities in 2006 to 4,092 fatalities in 2009. What we want to know is what is the average rate of change of the number of pedestrian fatalities. And of course, that would be with respect to time, right? So with respect to the year. So basically, if we were looking at a situation where we were using the standard variables, the x would be the explanatory and y would be the response variable. In this case, we're going to represent the horizontal axis using t for time or the year, and y, the response variable, will be n, which will be the number of fatalities. So basically, when you set up your table, which would normally look like this, where you would have x and y, etc. So now instead of x, we're going to use t, and instead of y, we're going to have n. So we can see that we can populate our table using, we know that in 2006, so that would be the year, the number of fatalities was 4,795, and in 2009 it was 4,092. So notice that this will represent N1, this will be N2, this is representing T1, and this will be T2, right? So that when we use the formula, we're going to use it in that order. So let's take a look at that in the next screen. All right, so notice, as I said, we're going to be doing n to, remember, if you remember the formula we discussed for rate of change, this is going to be n2 minus n1 over t2 minus t1, right? So notice n2 here is right there, 4092 minus n1. Remember, it's always the last result minus the initial result, or the final result minus initial result. So minus 4795 for n1, and t2 was the last year we were looking at, 2009, and the first year we were looking at for this study was 2006, right? So that's where this data comes from. Let me clean this now. So notice that the units up here are basically fatalities. How many fatalities, right? The unit down here is year, right? So year 2009 minus year 2006. So when we subtract that, notice we actually get a negative value. So this indicates the rate of change is negative. What does that mean? That means the number of fatalities have been going down. On average, notice that once we divide that, we get negative 234. So you always want to do this so that you get the unit rate of change, right? So this is how many fatalities per year. This itself is a rate of change, but it's telling you how many fatalities in 3 years, whereas this one is giving you a nice per average, average number of fatalities per 1 year, which is a better unit to look at. So they've been going down on average 234 per year. All right, so here we have another rate of change problem. Find the total cost of 12 karate classes and an enrollment fee is $158. The total cost of 20 karate classes and the same enrollment fee is $230. The charge per class is the same, meaning that enrollment fee regardless of the number of classes for which you pay. Find the rate of change of the total cost with respect to the total number of classes. So, for example, our axes, if we were to do a plot, instead of x, y, we may want to use n for the number of classes and c for the cost. And we're trying to find the rate of change of cost with respect to the number of classes, right? So if we were to do a table, instead of having x, y, right, we would have what? We would have NC, like that. And we know that 12, when n is 12, meaning the number of classes is 12, the cost is 158. And when it's 20 is the number of classes, the cost is 230. So notice that this will be, this is C1, that's C2, this is N1, and this is N2, like that. So when we try to find the rate of change, we know it's going to be the change in total cost. So it's going to be, according to the formula we had, it's going to be C2 minus C1 over the change in number of classes. So that'll be N2 minus N1. Notice C2 from our data is right there, 230, so that's where that comes from, minus C1, which is 158, divided by N2, which is 20, minus 12, which is right there, okay? So then we do that, and we can see that basically the cost is going to be $9 per class, because that is precisely what this rate of change is telling us. It's basically telling us how much we're going to be spending per class for this karate course. And this, of course, takes into consideration that fixed enrollment fee, which is charged regardless of the number of classes that are taken. For our next example, we're going to look at an association that involves a constant rate of change. It's a familiar rate, time, distance kind of situation. So suppose that a student travels at 50 miles per hour on a road trip, and let D be the distance in miles that the student can drive in T hours. Identify the explanatory and response variables. Of course, in situations like this, we consider T to be the explanatory variable. A change in time is what's changing the distance, so therefore D will be the response variable. We're going to construct a table, and of course our table, as you know, we always have the explanatory variable on the left and the response variable on the right of our table. So it'll have that kind of a shape, and we're going to calculate it for 0, 1, 2, 3, 4, and 5 hours. Okay, it's very useful in tables like this to actually do the following. Just write the units in the heading of each column. That way you don't have to repeat the units in every row. So this one will be in miles, like that. So let's go ahead and construct that table. So as we said, time will be our explanatory variable and distance will be our response variable. And of course, where these values come from for distance is from the familiar formula, distance equals rate times time. We know that the rate is a fixed 50 miles per hour. So therefore, for example, if t is 0, that implies the distance will be 50 miles per hour times 0 hours, right? So 50 times 0 is just 0. Hours cancel, so that's 0 miles, right? If t is 1, for instance, we get d equals 50 miles per hour times 1 hour. Again, the hours will cancel out here. Units should always work out properly, otherwise there is a problem with the formula. And here we get 50 miles. If t equals 2, we get d equals, very similarly, that doesn't change because it's a fixed speed, constant speed, times 2 hours. Again, hours cancel out, we get 100 miles. So that's where these values are coming from, okay? And of course, this goes on until the very end of the table. So for each time value, we go ahead and multiply it by 50 to get the corresponding distance value. Of course, this one is in hours. We multiply by miles per hour, and the hours will cancel, and we end up with simply miles in the distance column. All right, so there's our table. Now we're going to make a scatter plot. Today I want to go ahead and show you how to do that on ClassCalc. So let's go ahead and take a look. Okay, so we'll go ahead and add a table. And with ClassCalc, you have to make sure, let me bring it into better view here. Okay, so that looks better. We're going to go ahead and put in the explanatory variables in that x1 column. So we get 0, starting with 0. And then we hit the down arrow and put 1. And hit the down arrow again, 2, 3, 4, 5. It's very important with ClassCalc not to hit enter, because then it creates a new row and that would cause problems on this side. On this side you'll be okay, but once you get to this side, make sure you hit the down arrow after each value. So the first one will of course be 0, the next one will be 50 if you recall, and then 100, 150, 200, and finally 250. Now when you look at this graph, it doesn't really do us much good because everything is out of the window that we see. So you can either fix that manually, and it's good to know how to do that, so I will show you, or you could just simply hit that, right? That just puts it in a best fit zoom fit situation. But let's do it manually. It will learn a lot more when you do that. So here we're going to change our x limits from, let's say, remember my values of x start at 0, so I'll just go a little bit to the left of 0 to leave me some viewing space. So I'll just click there and select Control A or Command A on a Mac and turn that into, say, -1 maybe. And then I'll click in this next one and push Control A or Command A to highlight it all. And I just need to go just a little bit past 5 for best viewing, so I'll just go to 6. The y-axis, I need to go from 0 to 250, so I'll start a little bit below the y-axis. So let's say I go from negative, actually let me do this, Control A, so I go from -10, and here for the max, again hit Control A or Command A to highlight it all and just type maybe 300. Okay, that should be great right there. Notice we just captured all the points in the new window, and we didn't have them, see, in its previous state. So now we're using different scales, right? So 1 unit here is very different from 1 unit there, right? See, each of these are like half a point horizontally. Vertically, notice each of those tick marks represents 1, 2, 3, 4, 5, so 10 units. So it's not drawn to scale as we would put it, but it's a much better view, right? We can get to see it more effectively this way. But you have to be aware of the fact that in actuality, it doesn't really look like this. In actuality, it would look like if you go to the default zoom and start to shrink it, see, like that. So notice we're using the same scale on both sides. They almost look like they line straight, line up in a vertical fashion, where it's not actually completely vertical. But this is the reality of the situation when it comes to the graph that we're looking at, if we use the same scale. But it's not helpful for us to use the same scale, and we don't really need to either, because there's, one is representing time, the other representing distance, so they're not really the same exact kind of thing anyway. So what we'll do is we'll just hit the zoom fit, and now again it's the same thing we did manually. The zoom fit does that for you automatically. But I want you to understand, it's not a magic thing that this does. It kind of does what we did, and we actually did it better because we went a little bit to the left of 0 and a little bit above 5, and we did the same thing here on the vertical axis, which gave us a nicer view, kind of like this, right? So this yellow is hard to see. Let me go ahead and change that. All right, so there's our scatter plot. You can see that this is an exact linear association. So, and notice that it is also positive, right? The longer you've been driving, the greater the distance that you've covered, right? After 2 hours, you've gone 100 miles. After 3, 150. After 4 hours, you've gone 200 miles, etc. So, of course, we can do partial hours too, and that's where the line comes in that we're going to draw. So if we draw the regression line now, in this, it's actually quite simple. You just have to start typing lin, and it puts it in there for you already. So now we're just going to put X, and then we're going to hit Shift dash. Okay, that brings you to the subscript position, and we're going to put 1. And then in the next, we're going to put Y, and then again Shift dash to bring it to the subscript location, and then we put 1 as well. So there you see we have the regression line, and of course, it can go through all of the points because this is a perfect linear correlation, exact linear correlation. And of course, as you know, this is not surprising. You already knew that the coefficient of the correlation coefficient is going to be exactly 1 for a exact positive linear correlation. All right, so if we come back in here, we can now see the PowerPoint version of that, which is very similar to ours, right? They've highlighted what these points are, and of course we knew that 0, 0, 150, etc. So they all line up perfectly. We even saw the equation. If you recall, it's actually going to be y equals 50x. That's the best fit line, which is a perfect fit line actually, given that it will hit every point in the data set, right? Therefore, the name exact linear correlation. So you have, as you have probably guessed by now, a constant rate of change will yield an exact linear association, right? Well, it works the other way as well. If you have an exact linear association, that's going to be coupled with a constant rate of change. And we say that here. So this is just saying that in reverse. So basically, what we say from a logical standpoint, we say a constant rate of change. We put a double arrow, so we say if and only if, or is equivalent to an exact linear association. Okay, and that's how we categorize these. So now, in order to tie this in with the concept of slope that we are familiar from algebra, we'll go ahead and use the notation of the ordered pairs for the pairings of x1 and y1 and x2 and y2, and then we can define the rate of change of y with respect to x as rise over run. Now, if you look at the picture that we saw earlier in the video in the beginning, we had this scenario, and notice that if this is x1 and that's y1, then this point here is known as the ordered pair x1, y1 in the Cartesian coordinate system. And if this is the point x2 and that's the point y2, then this ordered pair will be the point x2, y2 in the Cartesian coordinate system. And this rise from here to here is what we call y2 minus y1, and this movement from here to here is what we call the run. So we say rise over run. Now, the double arrows here, they just mean this distance is the same as that distance which we saw over here. Normally, you'll just see an arrow pointing up and one pointing to the right, right? So I just want you to understand, we were just showing that this distance and this distance are the same exact distance. Now, in modern terminology, a lot of times we don't use rise over run anymore, because sometimes if the line is facing this way and the slope is negative, you may have a fall over run. So usually in modern terminology, we just say change in y divided by change in x. That's actually a much more relevant terminology for today's mathematical language. So we write the rate of change is equal to change in y over change in x, which is y2 minus y1 over x2 minus x1. And in more advanced mathematical settings, you may also see delta y over delta x. This notation using delta also indicates a change. So whenever you see delta used in mathematics, it usually indicates some kind of a change. It's just a triangular notation, but it's from the Greek letter that represents it is a delta. Let us look at another application. Here we're going to be estimating rates of change. A carat is a unit of weight for precious stones and pearls. The scatter plot and the model in the figure describe the association between the weights in carats of some diamonds and their value in Singapore dollars. Is the association positive, negative, or neither? And estimate the rate of change of value with respect to number of carats. I mean, obviously we can see clearly here that there is an association between weight in carats and the price, right? And it's a positive association, and it's very much linear, right? A very strong linear association here. So in order to come up with a best fit line just visually, you remember there is an exact way of accomplishing that, and that's what the linear regression function on the various mediums we've seen, such as StatCrunch or Desmos or ClassCalc utilize. But just if you want to do a visual line, we can draw a line. Notice that line right there would be a pretty good line that comes close to all the points. And notice that the line would go through these 2 points, point 1, 110. So basically a diamond weighing 0.1 carats being priced at 110 Singapore dollars, and 0.35 1040. So a diamond weighing 0.35 carats being priced at 1,040 Singapore dollars. So what we're going to do is we're going to use those 2 points and come up with the equation that we need. So here are the 2 points again, right? So basically all you have to do is just call one of the ordered pairs, like this one, x1, y1, and call this one x2, y2, as we show here. So then all you have to do is just do y2 minus y1, so 1040 minus 110 over 0.35 over 0.1, and this is what we obtain. And if we do the division, we get 3720. So remember, the units on the top were dollars, right? And the units down below were carats, right? So that means basically that the price is $37.20 per carat. So this is a nice example of using a linear model to estimate a given association. And again, it is an approximation. So basically we're saying if one piece of diamond weighs 1 more carat than another piece, it's going to cost $3,720 more than that piece. Now, to bring together the concept of direction of an association and rate of change, remember that if the direction is positive, that means the rate of change is going to be positive as well. The rate of change of the response variable with respect to the explanatory variable. And if the association is negative, the rate of change of the response variable with respect to the explanatory variable is going to be negative. Now we finally present this rate of change as the familiar slope formula which we recall from algebra, okay? And again, oftentimes, even in the algebraic concept, we would prefer to use change in y over change in x instead of this older terminology that we used to use. So here's another graphic similar to the one we saw before. Here we can see the one directional arrow, that would be the run, that would be the rise, and the slope is of course rise over run, because we're trying to find the rate of change of the vertical component to the horizontal component of these two changes. So always remember that. Change in y over change in x. So here we'll look at a simple example. We're going to find the slope of the line that contains these 2 points. Remember, call one of the pairs x1, y1. Think of the other one as x2, y2. We know that the slope of a line is given by the change in y over the change in x, right? So here we're going to have 5 minus 3 over 8 minus 2. The direction is important, so if you're doing y2 minus y1, you definitely have to do x2 over x1 down below. You don't want to switch directions suddenly and do y2 minus y1 up here and do x1 minus x2 down there. That would not give you the correct slope. So we end up with 2 over 6, which is 1/3. Okay, so this basically means for every change of 1 in the vertical direction, this line would have a change of 3 in the horizontal direction. We can see that visually by just plotting these 2 points, 2, 3, right there, and 8, 5. Now notice, for every rise of 1 in the vertical direction, there's a corresponding run of 1, 2, 3 units. See? So as this line makes its way to 1 unit further up, the horizontal distance that is traversed at the same time is 3. So that's why we say the slope of this line is 1/3. So 1 vertical change corresponding to 1 unit of vertical change corresponding to 3 units of horizontal change. So as far as categorizing positive and negative slopes, notice that a positive association is basically corresponding to a positive slope of the line associated with that association, and a negative association would correspond to a negative slope, right? So notice how here this is going, to get from this point to this point, you would go up and then to the right, but to get from this point to this point, you would have to go down and then to the right. If you only handle up-down movements first and then left-right movements, right? So this would have been maybe clearer if you had seen this piece over here and this piece going that way, right? So the point is, imagine if you can only go up-down first and then only left-right, what would you need to do to get from this point to this point? You would have to go up and then to the right, right? Same thing here. If you can only go vertically first and then horizontally, and those are the only possible movements, what would you have to do to get from this point to this point? Well, you would have to go down this much, right? And then to the right. So when you have to go down, we consider that a negative rise, right? Or a fall, same thing. So again, notice that if the response variable increases as the explanatory variable increases, that translates into a positive slope. If the response variable decreases as the values of the explanatory variable increase, then we see that that corresponds to a negative slope. Let's go ahead and find the slope of the line that contains these 2 points. Notice that we have a quick graphic of that here, and this line is obviously going to have a negative slope, so we'll verify that now. So we'll go ahead and think of the first point as x1, y1, and the second point as x2, y2, right? So the slope will be given by the change in y, or y2 minus y1, over the change in x. All right, so y2 is -4 minus y1, which is 2. x2 is 3 minus x1, which is -5. Be very careful here not to just write 3 minus 5. That's a very common error. You want to avoid that. It's x2 minus whatever x1 is. x1 happens to be -5. So 3 minus and -5. Of course, those two will make a plus, right? So it becomes positive. So we get -6 over 3 plus 5 is 8. So we get -3/4. Now, -3/4 shows you definitely the slope is negative. We expected that, right? So what does that mean? That means basically for every... the interesting thing is you can set it up in 2 ways. You can write it as -3 over +4, or you can write it as +3 over -4. Both interpretations will land you on points on the line. So let's say you start at 1 point, right, on this line. You can go 3 units down, right? And then, so starting there, you go 1, 2, 3, and then go 4 units to the right, and you'll end up with another point on this line. You see? So for every fall of 3 units on this line, every vertical fall of 3 units corresponds to a movement to the right, or a run of 4 units, horizontal units. So what if you interpreted it this way? Can you start on this line and then instead go up 3 units and then left 4 units and end up with a point on this line? Absolutely, you can. So you can go 1, 2, 3, and then 1, 2, 3, 4. There, you end up with another point on this line. So basically, this is the constant rate at which this line is decreasing, right? And there's one other interpretation. You can also look at it. Well, there are many interpretations, but one interesting one is you can think of it as -3/4 over +1 as well. So you can see that a movement of 3/4 down on this line would correspond to a horizontal movement to the right of 1 unit. So there's one other interesting interpretation of the slope with the case of a line like this. One of the things we'd like to be able to tell just by looking at the line is how steep is it, right? So we need some kind of a standard. The actual standard for slopes is the 45-degree line's slope. So that's the line that goes through 0, 0, 1, 1, etc. So this line, the 45-degree line, has, remember, if, let's say you want to go from this point to this point, right? So from 0, 0 to 1, 1, you have to go up 1, right 1, right? So the slope is 1, right? So the slope is 1. So we usually compare lines to this line, right? Notice that the closer the absolute value of a line is to that value 1, the closer it's going to look to either this line here or the counterpart with a slope of -1, like that. So basically, when you look at these two lines, you can quickly see this one is steeper, right? So think of the slope as a measure of steepness. The larger the absolute value of the slope, the steeper the line is, right? We say the absolute value because we also want to consider, say, a line like this, which has a negative slope, but that's also a very, very steep kind of fall. If you were to, say, be skiing on this, that would be a very, very steep slope, right? So we want to consider both positive and negative slopes that are very large. So that's why we look at the absolute value and determine steepness. So even though we can just look at these two lines and tell L2 is steeper, we don't actually have to just depend on our visual consideration. We can actually calculate it. So let's pick 2 points on L2. We'll pick two, we can pick any 2 points, but let's pick 2 points that are nice. What do I mean by that? They go through these corner points, if possible, right? So let's say we pick this point and this point on that line, right? Notice that to get from this point to that point, I would have to go up 1, 2, 3, and then to the right 1 unit. So notice the slope of L2, let's call it M2, is basically 3 over 1, which is 3, right? Now look at L1, right? L1 has a lot of simple points you can pick. So let's just pick these two, right? Notice to get from this point, I didn't want that. Notice that to get from this point to that point on L2, you would have to go up 1 and to the right 1, right? So notice the slope of L1, which we'll just call M1, is 1 over 1, which is 1. So as we expected, notice the slope of L2 is larger than the slope of L1. And you can see that it is steeper. Just imagine yourself climbing on these slopes as if they were mountains, right? Which one would be harder? This climb or that climb? See, you can clearly see climbing L2 would be harder. It's 3 times steeper than L1. So slope in the geometric sense is a measure of steepness of a line. So here we can see, notice these two, they have opposite values, but their absolute values are the same, right? So they would pretty much indicate the same kind of steepness, right? So think of it this way. If you were to climb this particular line going up like this, or climb this one going up from this direction like this, you would be dealing with the same exact level of difficulty. See what I mean? Or consider the one with the 1 and -1, right? It would be just as hard to go up this one slope, the line with the slope 1, as it would be to go up like this on this other line which has slope -1. So that's why the absolute value of the slope is considered when thinking about steepness. Notice that all the lines we've talked about so far have been what we call oblique. They have not been horizontal and they have not been vertical. So let's talk about what happens with the slopes of those lines, right? So here's an example. If we just pick these 2 points and look at them visually, let's see what happens. Okay, so notice here we have the point 3, 2, here we have 7, 2, and there's the line that goes through them. And so what kind of a change do we need? What if to get from this point to this point, right? What kind of vertical change is required? None, right? Therefore, the slope is literally 0 over whatever that distance is, which is 4. So therefore, the slope is 0. So using the formula would work as well. Just call this one, let's see, I need to bring up my grapher. Okay, so we know that m equals y2 minus y1 over x2 minus x1, right? So think of this as x1 y1 and this one as x2 y2. Notice we end up with 2 minus 2 over 7 minus 3. So we end up with 0 over 4, which is 0. So notice horizontal lines are flat. So, how much of a climb would it be if you were going along this line? There would be no climb at all, right? That would just be a flat road, all right? So that's why slope, again, gives you what? Measure of steepness. So it makes perfect sense that horizontal lines would have 0 slope. Okay, so what about vertical lines? What kind of slope would those have? Let's take a look at that, those 2 points on a graph. Okay, so here we have 3, 1, and here we have the point 3, 5. There's the vertical line that goes through them. So, of course, remember that to get from this point to that point, we know you just need to go what? You need to go up 4 units, right? From 1 to 5. But how much do you need to go horizontally? No change at all, right? So this time we get into trouble arithmetically. Here's how. We know that the slope is going to be given by the same formula as always, right? So now if we just look at this as doesn't make any difference which one you call x1 y1. Let me just go with this as x1 y1 and this one as x2 y2. So notice that y2 minus y1 becomes 5 minus 1, but the change in x, that's going to be 3 minus 3. So that's going to be 4 over 0. And of course, we know that this is undefined. So I'll give you a little tip. Vertical lines do not really have a slope because there's no numerical value we can give it, right? But just so you know, imagine you're climbing this thing, right? What do you think? How hard would that be? That's pretty much impossible, right? As far as climbing is concerned. If you were to try to climb this thing, you're in trouble, right? Well, it's that impossibility that makes the slope also undefined, right? So because the slope, we say one way of saying is that it's undefined, but later on you're going to learn the fact that this actually corresponds to infinity. So that's basically infinite slope, right? But for the purposes of us and our class, we are going to consider vertical lines as having no slope or undefined slope. Okay, I was just giving you a little bit of hint of what you will see in future math classes if you continue. So to summarize, a horizontal line has a 0 slope and a vertical line has undefined slope or no slope. No slope should not be confused with 0 slope. 0 is a perfectly good number, okay? Whereas no slope means undefined slope, which is not defined. So this one, yes, it has a slope and it's 0. This one, it does not have a slope because we consider the slope to be undefined. All right. That pretty much wraps up our lesson. We'll take a look at a few of the problems you may encounter on homework together, and that should do it for us for today. All right, so in this problem, we're looking at an airplane's altitude, which is declining steadily by 28,025 feet over a 19-minute period, and we wanted to know the rate of change of the airplane's altitude per minute. So basically, the rate of change is going to be the change in altitude divided by the change in time, right? Now, they're not giving you two separate instances, but they're giving you the actual change. So this is easier because we're just going to use the values given. Except be really careful because they're saying the altitude is declining. So the change in altitude is going to be negative 28,025 divided by over a 19-minute period, so 19. And remember, this is going to be in feet per, notice, per minute. Right there. All right, so if you calculate that, you'll get negative 1475 feet per minute. So they tell you how much it had declined in altitude over 19 minutes, but they wanted you to find out how much that translates to in feet per 1 minute, which is what this rate of change is giving us. So here's another rate of change problem. This time we're looking at the percentage of people in some country who have trust in newspapers declining approximately linearly from 40% in 2000 to 29% in 2005. And we want to know the rate of change of percentages of the people in that country who have trust in newspapers per year, right? So a rate of change. Again, if you think you know how to do it, you should do it and then come back to the video. And this goes with every single problem that I do in these videos for you. So notice that if we were to form some ordered pairs, which would be good, a good thing to do, and create a table, we would get something like this. We would want the year and the percentage of the people who trust newspapers in the next column, right? So maybe if we're going to use variables, we'll use like T and P, right? And we will have for the year 2000 corresponded to 40% trust in the newspapers, and in 2005 it had gone down to 29%, right? So we know that the rate of change is going to be, remember, you can think of this as T1, this one is T2, this one is P1, and this one is P2, okay? So basically it'll be P2 minus P1 over T2 minus T1, right? So we're going to have 29% minus 40% divided by 2005 minus 2000. So then we go ahead and take care of that. So we get 11% over 5, which is basically 2.2%. And remember, the units are going to be, this is down here, we're going to have over 5 years, right? So the final units will be percent per year, like that. So basically, the rate of change of the percentage of people who trust the newspaper is negative 2.2 percentage points per year. It means every year it's going down about 2.2 percentage points. That's what is the significance of that rate of change. All right, so here we have in this problem a stock that is worth $5 on October 1st, and that its value increases by $3 per week. And let V be the stock's value, so that's going to be the response variable in dollars, and T is the number of weeks since October 1st, right? Complete the parts below. So notice that the explanatory variable here will be the number of the T, which represents the number of weeks since October 1, and the response variable is going to be the value of the stock, right? So remember, starting at October 1st itself, that would be T equals 0, right? How many weeks after October 1st is October 1st? Well, 0 weeks, because that's when you're starting, right? So at that point, we know the stock's value was $5, right? And remember, it's going up $3 a week, right? So when will it be? How much will it be a week later? $8. 2 weeks later, well, go up by 3 again. 3 weeks later, go up by 3 again, etc., all the way down to here. So we're going to use technology to construct the scatter plot, and if we do that, you know, by now you should be very comfortable with that. You'll come up with this scatter plot. Notice that we have an exact linear association, and it is positive. And notice, of course, there are no outliers. And since it's an exact linear association, what's the value of R? Of course, it is 1. And of course, this means it's linear and positive. Draw a model in the scatter plot. Of course, if we're going to draw a model here, that's going to be a very perfect model. It's going to be a straight line that's going to go right through it, right? Explain how this exercise suggests that if the rate of change of one variable with respect to another is constant, then there is an exact linear association. Because remember, when it's a constant rate, when you do the scatter plot, they become perfectly linearly assembled, and therefore the function describing them will be a straight line, and therefore it'll be an exact linear association. All right. Here we're given a pair of points. We want to find the slope and then decide whether it's increasing or decreasing, of course. So remember, just give those names like x1, y1, and x2, y2. The slope is just going to be y2 minus y1 over x2 minus x1, which is going to be 4 minus 8 over 9 minus 7. So we get negative 4 over 2, which is negative 2. And of course, a negative slope indicates a decreasing line. All right. All right, so when you have all negatives, just be slightly careful. It's very easy, just like any other, but just be a little bit more careful, okay? So here we have x1, y1. Okay, we shouldn't cover the original problem. And this one will be x2, y2. So our slope is going to be just like before, y2 minus y1 over x2 minus x1. So we get -3 minus quantity -6. That means you have to parenthesize it, okay? So downstairs we get -6, that's x2 minus -4. And keep in mind that those two are going to result in a plus or positive, and so will those two. So we end up with -3 plus 6, which is +3, over -6 plus 4, which is -2. Normally we would like to write that with just the negative on the side, so we get -3/2 like that. And this line would of course be decreasing. Think of this one and see if you can think of the slope before you come back to the video. Pause it, see if you think you can find the slope, and then come back. All right, so again, we're going to have x1, y1, and x2, y2. So the slope is going to be y2 minus y1 over x2 minus x1. So it's going to be -6 minus -1 over -7 minus -7. Both of those will turn into addition problems, and we end up with -6 plus 1, which is -5, over -7 plus 7, which is 0. So this is going to be undefined. So you can see we were dealing with a vertical line, and of course that's easy to see because the x value is the same on both of them, so they're going through the line that goes through those 2 points will be a vertical line. You should do a quick sketch of it to convince yourself of that fact. So if you want to find the slope of a line using nothing but a graph, try to find 2 points on the line which go through these nice little corners here, right? Like there or there, etc. So we can see that in this particular case, for example, we can pick this point and say this point, right? So now we just have to see what we need to do to get from one of those to the other. So from, say, this one to that one. Notice we would have to go up 2 units, right? So remember, slope is the vertical change divided by the horizontal change, right? So the change in y is going to be +2, and the horizontal change is going to be 1, 2, 3 units, right? So over +3, so the slope here would be 2/3, right? So just very simple, make sure you understand that. So in a problem like this, you don't really have to find the slope because they're not giving you any exact grid which you could use to really find the slope, but they just want to know if you think this is going to be a positive slope, negative slope, zero slope, or undefined slope. And clearly this one, as the x values increase, the y values decrease, so this one would be a negative slope. All right, so here they want you to pick a line that meets certain descriptions. They want it to be increasing and nearly horizontal, right? Notice that this is out because it's decreasing. This is out because it's flat. The slope here is 0. These two are the only increasing ones, but they say nearly horizontal, so this is the only one we could use. All right. Then they want you to actually find the slope of the line that you picked, right? So let's make it bigger. So notice, to get from, say, this point to that point, right? First, we need to determine what each tick marks represent. I noticed that there is 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 tick marks between 2 numbers, break them into 10 equal parts, right? So each tick mark is marking out a single unit. And here though, 1, 2, 3, 4, 5, 6, 7, 8, 9. So each of these are actually going to be 2 units, right? Because we have 10 equal parts making 20, so each has to be 2. So be very careful with that. Okay, so notice that we go up 1 to get from this point to that point. If we can only go up down first and only left right after that. So notice you'd have to go up 1. So the slope, which is change in y over change in x, is going to be positive 1 over, how about the change in x? Notice that's going to be 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2 is what? 16. So the slope is 1/16. Okay? We type that in. And we should be done with the problem. Okay? Very simple. All right, so let's let this one be the last problem we'll look at today. So here we want to sketch a line with a slope of 2 and another with a slope of 4. Does the steeper line have the greater slope? Well, there are different ways we can go about doing this, right? There are countless lines we could do, right, and graph, but the easiest way to get one that has a slope of 2 is just start at the origin, right? At 0, 0. Then just go, you want the slope to be 2, that means go up 2 and then over 1. Right there. Now, we also want to graph one with a slope of 4. So again, we could go to any point, but we might as well go with the simplest one. Start at the origin. This time we're going to go up 4 and over 1. See? Now, they're asking us, does the steeper line have the larger slope? This is the steeper line, right? And notice that's the one that had the slope of 4, so definitely does have the greater slope. All right, so that should do it for us. I think you should be able to handle the homework now, and make sure that you get it all done in time so that we can be ready for the test. Stay safe and see you at the next video.